Okay, we are now going to put our attention on series. Now, a series is just the sum of the terms of a sequence. So, to be clear, a sequence is a list of terms like A1, comma A2, comma A3, dot, dot, dot. A series is the sum of these things, and it's an infinite sum. So we often would use, of course, the sigma notation. How can we add an infinite number of things together in a meaningful way? Well, it's not always possible to do that. For example, if we look at this particular series here, this is 1 plus 2 plus 3 plus 4 plus dot dot dot. We would say that this series diverges because the sum of the terms clearly goes to infinity, right? The farther you go out, the more you're adding stuff onto this thing. So series that are divergent, we're basically going to just not be interested in. We're going to kind of throw them away like they're garbage. What we're more interested in are convergent series. So something like this, for instance. So when n is equal to 1, we get 1/2, then 1 over 2 squared, 1 over 2 cubed, 1 over 2 to the 4th, and these terms are like 1/2 plus 1/4 plus 1/8 plus 1/16, and the sum of this series is actually 1, right? I mean, imagine you had a glass of water that was empty, and then you filled it halfway up with water, and then you added a quarter of what was left, so now you're at 3/4, and then you added an eighth of what was left, and you just kept doing that. Well, if you stopped at any given point, you would not have 1. But if you took the limit of that process, then you'd get exactly 1 full glass of water, so 1. Okay, so we do need a rigorous definition of convergence and divergence. So let's figure one out right now. So for any given series, AN, let's consider its associated sequence of partial sums. Okay, so a partial sum of a series is just the first n terms added together, but not going all the way to infinity. So like the third partial sum would just be a1 plus a2 plus a3. And the seventh partial sum would be a1 plus a2 all the way up to a7 added together. Okay? So the actual sum of a series is just kind of the infinitieth partial sum. So, okay, so that creates a new associated sequence. For instance, we could say S1 of this new sequence is just the first partial sum of the sequence, A1. S2 is A1 plus A2. S3 is A1 plus A2 plus A3. All the way down, keep going. The general term would be the nth partial sum, which would be A1 plus A2 plus A3 plus dot dot dot, all the way up to and stopping at AN, adding those together. So if you have a series AN, there's an associated sequence of terms made up of the sequence of partial sums. Okay? Now, if this sequence here is convergent by the definition of sequence convergence from the last section, then we would say this series here is convergent. You know what? Let's define this a little bit better than that. So what are we seeing here? Well, we're defining this infinite series to be the limit of the finite series. So it's sort of like how we would define an improper integral. So in other words, we have a finite series that starts at 1 and ends at capital N. And those are always defined because you can certainly add up a finite number of things. but we're taking capital N to infinity, and that's the definition of this infinite series. Okay, so we would say that this series converges if the limit exists and is finite. And in this case, the limit itself is the value of the sum. If the limit does not exist or evaluates to plus or minus infinity, then we say the series is divergent. And like I said earlier, we only are interested in convergent series. Divergent series are basically garbage to us. So we're going to spend several of the next sections simply picking up different tools that will help us establish whether or not a given series is convergent or divergent. Okay, so the first really important type of series we're going to see is a kind of series called a geometric series. So a geometric series is just a series where from one term to the next, you're just multiplying by a constant. So it looks like this. So notice that each term just has an additional factor of r as you go to the right. And this is called a geometric series. So geometric series are particularly nice for a number of reasons. One of them is that we can determine the conditions for its convergence very easily just by consulting that particular r value. So let's see how this works. So, all right, well, we know that a series is convergent if the limit of its partial sums exists and is finite. So let's look at the partial sums of a geometric series. We're going to do that by defining S capital N to be the nth partial sum. So instead of this going from 1 to infinity, we're going from 1 to capital N. All right, so this is the nth partial sum of, well, any series, but in particular, for a geometric series, it looks like this. A plus AR plus AR squared plus AR, and then the last entry would be N minus 1 with capital N there. All right, so what we want to do is take the limit of this expression as capital N approaches infinity. However, this expression is written in what's called an open form, which means you can't easily take the limit of it because you've got these like dots in the middle. So what we want is a closed form. So in other words, an expression without like this dots in the middle. So for a geometric series, it's not hard to achieve a closed form. What we're going to do is we're going to multiply both sides of this by r. So we're going to have r times Sn is equal to r times this thing. So distributing the r on the right, we're going to get ar plus AR squared plus AR cubed plus dot 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 AR to the capital N. Okay. Well, let's move this guy down a little bit because I want to put right above it, I want to remind us what Sn is. Sn is A plus AR plus AR squared plus dot 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 plus AR to the N minus 1. So the reason why we're writing that there is so that we can now subtract Rsn from Sn. And you're going to see that we're going to get this line minus this line. Okay. However, most of the terms are going to cancel. So we're going to get the A, but then we're adding AR and we're subtracting AR. And we're adding AR squared, and we're subtracting AR squared. And we're adding AR cubed, which isn't written, but it's in the dots, and we're subtracting AR cubed. So we get all of this cancellation, and even this guy cancels with the one that's not written that's right before ARN. And so what we get is simply minus AR to the n. Okay, remember, we're after a closed form for S capital N. So if we factor it on the left, and we can also factor A out on the right, and now divide both sides by 1 minus R, we get our closed form. So what does this mean? Well, it means exactly this, that if you want to add up the first 100 terms of some geometric series, then it's exactly equal to this for whatever values of A and R you want. Note that this only holds provided that R is not equal to 1. All right, we'll worry about that case later. Now, let's recall that what we're really after is checking to see if this series converges. And we know that that series is defined to be this limit. All right, but this here is just Sn. So what we're really doing is we're calculating this limit of the closed form for Sn. So what is the answer to this limit problem? Well, this is going to depend on the value of R. We would get convergence if this R to the n approached 0. So what are the conditions on little r so that R to the n approaches 0? Well, that would occur if little r were between -1 and +1. So this limit would evaluate to a over 1 minus r, which is the form we'd get if that R to the n went to 0. And this would occur if little r is between -1 and +1. Another way of writing this is saying the absolute value of R is strictly less than 1. So what this means is if you have a geometric series and your little r is strictly less than 1, then the geometric series converges. And moreover, the sum of the series is a over 1 minus r. On the other hand, if the absolute value of little r is greater than or equal to 1, then we would say that this series is divergent. So let's summarize this. Okay, so this is often referred to as the geometric series test. And let's see it in action on a few examples now. All right, so here we have a series, and we want to see if it's convergent or divergent. And if it's convergent, let's find its sum. Very good. So first, let's convince ourselves this is indeed a geometric series, because honestly, most series are not going to be geometric. So what is it that makes this a geometric series? And that is that from one term to the next, you are multiplying by the same thing as you go along. In other words, any random term divided by the immediate previous term will always give you the same thing, no matter where you choose those terms. So 16/9 divided by -8/3 will be the same thing as -8/3 divided by 4. And that's the R value of the series. Okay, here it looks like to go from one term to the next, we are multiplying by -2/3, multiplied by -2/3, multiplied by -2/3, etc. So we can see that our R value is -2/3. That tells us this is a geometric series. All right, well, is the series convergent or divergent? So let's check the absolute value of R. Absolute value of R is 2/3, and 2/3 is less than 1. So therefore, the series, we'll just call it AN, is convergent. There we are. Okay, so a little note about articulation. it's very important that you demonstrate your thought process. So don't just conclude out of the blue that a series is convergent or divergent. You need to give some justification. Here, it's because specifically the absolute value of r is 2/3, and 2/3 is less than 1. That's why the series is convergent. Now, the second part of the problem is, if the series is convergent, then find the sum. Okay, so the sum of the series is a over 1 minus r. Well, we've already got the r value. That's negative 2/3. Well, the a value is even easier to get. It's just the first term of the series here. So it's 4. So this is going to be 4 over 1 minus negative 2/3. All right, let's multiply top and bottom by 3. And we'll get 12 over 3 plus 2, which is 12 over 5. So that is the sum of the infinite terms of this series. Now, never write down the sum of a series or work out the sum of a series until after you've established that the series is convergent. But we'd already done that, so we're good to go into the sum here. All right, let's do the same thing for this one. Now, this one's given in sigma notation, but we can recognize that it's got the form of a geometric series because you have essentially the base raised to some version of n. So all we need is the r value to see whether or not the series is convergent or divergent. So what's the easiest way to find the r value when you're looking at the series in sigma notation? This is not a form where it's easy to see anything at a glance. However, we could start to play around with this because we know that the form of a geometric series is ar to the n minus 1. So we could kind of force this into that form and see what our r and our a value is. So for instance, 2 raised to the 2n, for goodness sakes, that's just 4 to the n. And 3 to the 1 minus n is 1 over 3 to the n minus 1. Okay. Well, wouldn't it be nice if we had 4 to the n minus 1 as well? Because then we could combine it with the 3 and we'd have 4/3 to the n minus 1, and that could be our r value. Well, we could easily do that by just splitting 4 to the n into 4 times 4 to the n minus 1 over 3 to the n minus 1. And then we have 4 times 4/3 to the n minus 1. And aha, we can now see that our r value is 4/3. And in fact, our a value, although we aren't going to need it because this is going to turn out to be divergent, our a value is also evident. It's equal to 4. However, like I just said, this is a divergent series because we have the absolute value of r, which is 4/3, that is greater than or equal to 1. So since the absolute value of r is 4/3, and that's greater than or equal to 1, the series is divergent. All right. Now let me quickly show you a shortcut for getting a and r as well. If you know a series is geometric, you can get the a value by just plugging in the first term of the series, because the first term of the series is always a. So if we let n equal 1 in here, we're going to get 2 squared, which is 4, times 3 to the 0. So that's 4 times 1. That's the first term of the series. So there's a. The second term of the series is always going to be a times r. So if we let n equal 2, we're going to get 2 raised to the 4, so that's 16, times 3 to the 1 minus 2, so that's 3 to the negative 1, which is 1/3. So we can see there's our a, which is 4, and there's ar. So taking ar, 16/3, and dividing by a, which is 4, you're going to get 4/3. That's our r value. So that's another way of kind of hacking through this to get at your R value if you don't want to manipulate the actual factors within the series. Okay, well, what about this series right here? So, well, let's write out the first couple of terms. If we let n equal 0, and notice this one does start at 0 and not 1, we're going to get e to the 0 over pi to the 1. So there's our a value. What we really want is r, of course. So let's let n equal 1, which is the second term of the series. So we're going to get e to the first power over pi squared. And then there's more stuff after, we don't care. So here's our a. And this is AR. So taking the second term and dividing by the first term, you're going to get your R value. So R is E over pi. Okay. So the absolute value of R is E over pi, and that's less than 1 because E is 2.7 and pi is about 3.14. So since we have an R value here whose absolute value is less than 1, the series converges. And now that we've established the fact that the series converges, it's worth calculating its sum. We're allowed to do that. So the sum is a over 1 minus r. A is 1 over pi. R is e over pi. So we get 1 over pi minus e as the sum of that infinite series. All right. All right, this one's a little bit different. Here we are interested in finding the specific values of x for which the series will be convergent. So it's almost like saying, let's call this a function, and what's the domain of that function? So for example, f of 5, we could see would be n equals 1 to infinity of letting x be 5, we'd get 0 to the n over 3 to the n, which of course would just evaluate to 0 for every term, and this would be 0. So f of 5 is 0 on this function, right? Whereas f of 4 would be n equals 1 to infinity, and 4 minus 5 is negative 1 to the n over 3 to the n. So this one would be like negative 1/3 plus 1/9 minus 1/27 plus 1 over 81 minus blah, blah, blah. So whatever that adds up to, well, that's a geometric series, so we could figure that out. So in fact, this is our very first taste of using a series to represent a function, which, as I said at the beginning of the last section, when I introduced this entire concept, that's where we're headed, right? We want series representations of functions. Okay. Again, all we're interested in here is the x values for which the series converges. So in order to answer that question, what we're going to do is recognize that this is the form of a geometric series, so we'll extract our a value and we'll extract our r value, and we'll see what the conditions are for r that make the series convergent. So simplest thing to do is just write out the first couple of terms of the series. So the first term is n equals 1, so that would be x minus 5 over 3. The next term would be n equals 2. So it's just that squared, and so on. Okay, well, we can see that a is x minus 5 over 3, and r is actually exactly the same thing, x minus 5 over 3, because as you just go from one term to the next, you're multiplying by x minus 5 over 3. So the series will be convergent when the absolute value of r, which is the absolute value of x minus 5 over 3, is less than 1. So we're just going to solve that inequality for x. All right, well, let's distribute the absolute value across the quotient, which you're allowed to do, because 3 is positive. Multiplying both sides by 3, we get absolute value of x minus 5 is less than 3. And that is equivalent to saying that x minus 5 is between -3 and +3. So if we just add 5 to all sides of this, we're going to get 2 is less than x is less than 8. And those are the bounds on x for which the series is convergent. So we'll say the series is convergent when x is between 2 and 8, strictly between them. Or you could say when x is in the interval 2 to 8. All right, the second part of the question said, find the sum of the series assuming convergence. So the sum is a over 1 minus r. Well, we calculated a to be x minus 5 over 3, and we also calculated r to be exactly the same thing. So we'll just clean up this thing. Okay, so there's the sum of the series. And you can see definitely, like we saw earlier, when x is equal to 5, well, you're going to get 0. Okay, so like I said earlier, not every series, in fact most series, are non-geometric. So we're going to need a lot more in the way of tools in order to determine whether or not a random series that we come across is convergent or divergent. So what we're going to see right now actually is a very specific type of series that we can work on directly. And these are going to be called telescoping series. And you're going to see why they're called that in a moment. So let's go right into an example. So we're going to investigate this series right here. Now this is not a geometric series, but let's look at its first few terms just to get a sense of what it feels like. So when n is equal to 1, we're going to get 1 over 1 times 2, so that's 2. And then the next term is 1 over 2 times 3. And then the next term is 1 over 3 times 4. And then 1 over 4 times 5, etc. So yeah, this is like 1/2 plus 1/6 plus 1/12 plus 1/20, etc. So who knows whether this even converges, and if it does converge, can we figure out what it adds up to, what the sum is? So before we go into this one, I want to actually comment that finding the sum of a series in general is very difficult to do. We can do it easily for geometric series and for a very small case of non-geometric series like this one. But most series we come across, we will not be able to find the sum. We will only be able to simply classify them as convergent, meaning they behave well in the universe of calculus, or divergent, meaning they don't behave well. This one we will be able to find the sum. So let's start by finding its partial sum. Again, this step right here is the one that's usually very difficult to do. So the partial sum is simply n equal 1 to capital N, not to infinity. So we're stopping at somewhere down the line, say the first 1,000 terms, or even the first billion terms is technically a partial sum. Now the trick is, if you've got this particular type of form here, you can use partial fraction decomposition to separate it into the sum or difference of two terms. So using partial fraction decomposition, we can write this one as 1 over n minus 1 over n plus 1. Now I'm not writing out the details of the partial fractions, but you would of course get a over n plus b over n plus 1, and you could work it out, and this is what you would get. The reason why we want to write it this way is because now we're going to write out the terms. So when we let n equal 1, we're going to get 1 over 1 minus 1 over 2. So this is the first term of the series, the n equal 1 term. The n equal 2 term is 1 over 2 minus 1 over 3. The n equal 3 term is 1 over 3 minus 1 over 4. Okay, so this is just going to continue, but it's not going to continue forever because this thing's going to stop. Why don't we stop right here? So this will be the nth term, and this will be 1 less than the nth term. So the nth term is 1 over capital N minus 1 over capital N plus 1. And the guy 1 less than that is going to be 1 over capital N minus 1 plus 1 over capital N minus 1 plus 1, which is capital N. So this is the open form for the partial sum Sn. Of course, we always want to try and find a closed form, and this only occurs if we can get some super magical cancellation to occur, which is going to happen, because look at this. Negative 1/2, positive 1/2, those cancel. Negative 1/3, positive 1/3, those cancel. Negative 1/4, and while we didn't write it, we know the next term would be a positive 1/4. And even this guy cancels with the one right before it. This guy cancels with, whoops, this was supposed to be a minus here. So now it cancels with the guy next to it. And this last term right here doesn't cancel with anything. It would with the term that would come after it, except we stopped because this is a partial sum. However, we now do have a closed form for the partial sum. The surviving terms are simply the first term, which is 1, and the last term, which is negative 1 over n plus 1. You can see why it's called a telescoping series. It's like a collapsing telescope. All the terms canceling look and feel kind of like a collapsing telescope, where once you've collapsed a telescope, you're just left with the right and the left ends of it. I hope these special effects hold up over the next few years. All right, well, the original series here is defined to be the limit as n approaches infinity of the finite series, the partial sums. And of course, this is just Sn here. And our Sn is 1 minus 1 over n plus 1. So this limit evaluates to 1. 1 is a finite number. So we can conclude that this series is convergent. And moreover, its sum is the limit of the partial sums, which is 1. Okay, so here we have a series that's clearly in 2 parts. So what we're going to do is investigate both parts of this. So let's first talk about this series here. N equals 1 to infinity of 5 over n plus 1. Well, just like you can with an integral, you can extract a constant from a series. So this is really like 5 times the series n equal 1 to infinity of 1 over n plus 1. Ah, yes, but we know a lot about this series because we just established that this series converges and that its sum is 1. So we can say the series converges to 1, in fact. So this is equal to 5 times 1, which is 5. All right, what about the other one? Well, this guy right here, this is a geometric series. So we can see that the first term is 1/3, and then the next term is 1 over 3 squared, and then 1 over 3 cubed, etc. So here we can see that it has an a value of 1/3 and an r value of 1/3, because we're just multiplying each term by 1/3 to get the next term. So since the absolute value of r is 1/3, which is less than 1, this series converges. And its sum, which is a over 1 minus r, would be 1/3 over 1 minus 1/3. So we get 1 over 3 minus 1, which is 1/2. Okay, very good. So we can now say that both parts converge, and therefore this series here is convergent. And its sum is just going to be the sum of the other two series of sums added together. So that's going to be 5 plus 1/2. Well, that's 11 over 2. All right, we are now going to see a series that is so special that it has its own name, and that's the harmonic series. So harmonic series is not a category of series like geometric series or telescoping series. It's just the name for one very specific, very important series. And that is this series. It's simply the series 1 over n. So the first term is 1, then 1/2, then 1/3, 1/4, and so on, all the way down the line. So this is called the harmonic series. What's surprising about the harmonic series is that it's a divergent series. If you start to add the terms of the series, the terms themselves approach 0, meaning the 1/billionth term would be 1 over 1,000,000,000, right? A 1/trillionth would be 1 over 1,000,000,000,000. And so if you're adding up terms and you're considering the partial sum, well, when you get out to 1,000,000,000,000, you're adding 1 divided by 1,000,000,000,000, which is basically like 0. It's very, very small. And then you're adding 1 over 1,000,000,001 and 1 over 1,000,000,002, and these are so small that they wouldn't really be affecting the grand total very much as you're adding them on the pile. However, astonishingly, this is a divergent series, meaning that if you take the limit of the partial sums, you will get infinity. And to give you a sense of how incredibly slowly this series diverges, if for every second the universe has been in existence, okay, which is about 4 times 10 to the 17 seconds. If for every second the universe has been around, we've added a term of the harmonic series. So 1 second after the Big Bang, we had 1. And then 2 seconds after the Big Bang, we were at 1.5. And then 3 seconds after the Big Bang, we added a third to that. And 4 seconds after, we added 0.25 to that, and so on. And we kept doing that. The number we'd be at right now would be about 41. We're only at 41 right now. And yet this is a divergent series, meaning the sum ultimately goes to infinity. And at this moment, what are we adding on the pile? Well, numbers that look like that. 1 over that huge thing. So this is a tiny, tiny, tiny fraction. And then a second later, we're adding that again. And a second later, we're adding that again, and so on. So just think of how disgustingly long it would take for this thing just to get to 100 or 1,000 or 1,000,000, and yet it will, because this is a divergent series. So let's see why this is a divergent series. Now, what we're going to do is we're going to sketch the graph of 1 over x. This is 1 unit right here, because 1 over x goes through the point 1, 1. However, what we're really after is the area of this square. Well, that's a 1 by 1 square, so it has an area of 1. Now, f of 2 is 1/2, so this square, or a rectangle in this case, has a height of 1/2. So the area of that rectangle is 1/2, because it has a width of 1 and a height of 1/2. Then f of 3 is 1/3. So this particular rectangle has a area of 1/3, because it's got a height of 1/3 and a width of 1. In fact, all of these are going to have a width of 1, so their height is just going to be 1 over whatever it is, right? So This guy has an area, this guy has an area. So this is an area of 1/4. This is an area of 1/5, etc. Now, would you accept that the sum of the harmonic series, 1 plus 1/2 plus 1/3, etc., is represented visually by the areas of these rectangles? So the sum of all of these areas would be equivalent to the sum of the harmonic series. And would you further accept that the sum of the rectangles would be greater than the precise area under the curve, because the rectangles are always a little bit taller than the curve, which means that we could say that the terms of the harmonic series exceeds the integral from 1 to infinity of the function 1 over x dx. All right, well, we could work this integral out. It's an improper integral. We're good at those. Except that this limit evaluates to infinity, which means that the sum of the harmonic series is greater than an integral whose area diverges to infinity. And so our only conclusion is that the harmonic series is divergent. All right, let's change gears a tiny bit and come up with some theorem that's going to help us get some information about the behavior of a series. Let's say I gave you this series here, and heck, let's just say we added up 5. N equals 1 to infinity of 5. Now, this is 5 plus 5 plus 5 plus 5 plus do. Okay. I think anybody could look at this series and immediately conclude that this is a divergent series, right? There's no way that this series could add up to a finite number. Even if you thought, no, I think it's going to add up to 85. Well, then the next term is going to be plus 5, so you're already at 90 and you're way away from 85, right? This is just going to add up forever. So this is going to go up to infinity. Okay, so this series is divergent. Well, what if we had something like 5n over n plus 3? Well, what's the first term of this thing? We're going to get 5 over 1 plus 3 is 4. And what's the second term of this thing? Well, we're going to get 10 over 2 plus 3 is 5. And what's the third term? Well, we're going to get 15 over 6. And then we're going to get 20 over 7. Does this converge or diverge? Well, we know when we have a series that's 5 plus 5 plus 5 plus 5, we know that's going to be divergent. But what's really going on here? Let's plug in n equals 1,000,000. If we plug n equals 1,000,000 in, we're going to get 5 million divided by 1,000,003. All right, well, that's basically 5, right? So the next term after that's basically 5. And the next term after that's basically 5. So this is a series also where we're just adding 5 plus 5 plus 5 plus 5 plus 5. So yeah, this is going to be a divergent series. So what we get is something called the test for divergence, which is that if you can see the terms of a series are approaching anything besides 0, you get to conclude that that series is divergent. So let's consider the series with the terms an. If you evaluate the limit of the terms themselves, and you get anything besides 0, you get to immediately conclude that the series is divergent. So in both of the last cases, we had that limit evaluating to 5. In the first case, it was just literally 5. In the second case, if we evaluated that limit, right, so that would have been the limit as n approaches infinity of 5n over n plus 3. Well, you evaluate this limit, and you're going to get 5. So 5 is not equal to 0. Therefore, this series here is divergent. All right. Now, what about if you evaluate the limit and you do get 0? Does that mean the series is convergent? Unfortunately, no. If you evaluate this limit and you get 0, then the test for divergence is inconclusive. Okay, so one of the most common errors that I see is students working out the test for divergence and then getting the limit equaling 0 and going, ah, well, it must be true that this series is convergent, which is false. We don't know. We can only conclude that the divergence test is inconclusive, which means we need to just do something else. We learn nothing. Think of it like if a person's not in California, then that person's not in Orange County, right? That's true. But the converse of that, if a person is in California, can you conclude that that person's in Orange County? Well, no. Whether or not that person's in Orange County is inconclusive. All you know is they're in California. Big deal. So you cannot just assume the converse is true. Of course, a counterexample would be the harmonic series. Look, the terms of the harmonic series approach 0, but the harmonic series is divergent. Okay, so we're going to show that this particular series is divergent. And we're going to do that by taking the limit of its terms. So the limit as n approaches infinity of an is the limit as n approaches infinity of n cubed over 3n cubed plus 2. Now the form here of this limit is infinity over infinity. And again, we are not allowed to use L'Hopital's rule on sequences and series. You can, if you like, create a differentiable f of x cubed over 3x cubed plus 2, and then take the limit of that, and then you have free reign to use L'Hopital's rule. But remember, this is a purely algebraic limit, so we don't need L'Hopital's rule anyway. We can just compare the degree of the numerator and the denominator. These have degree 3, both of them. That means that the limit evaluates to the leading coefficient of the numerator divided by the leading coefficient of the denominator. So this limit evaluates to 1/3. Okay, so this is a series where if you go far enough out, you're basically adding 1/3 at every step. So it doesn't matter how the series starts, it's kind of like plus 1/3, plus 1/3, plus 1/3, right? Or numbers very close to 1/3. So when you do that an infinite number of times, obviously this can be divergent, right? This is going to add up to infinity. So we can draw our conclusion. What is it specifically about 1/3 from which we can draw our conclusion? It's not 0. Remember, always justify your conclusions. So 1/3 is not equal to 0. Therefore, this series is divergent. We also need the sigma here, referring to the series, because without the sigma, you're talking about the sequence, and actually, the sequence an is convergent. We just showed it goes to 1/3, but that's irrelevant. The series is divergent. So it's important at this stage in math that we're unambiguous with our reasoning and our articulation of our conclusions. All right, so let's test this series here. And again, we're going to do that using the test for divergence. So we're going to take the limit as n approaches infinity of an. So this is the limit as n approaches infinity of arctangent of n. And this is one of those limits where you either understand the behavior of inverse tangent well enough to answer this, or you don't. So let this be the moment, if you don't know it yet, that you learn it. The answer is pi over 2. A really neat way of seeing this is by imagining a triangle, and we're going to call this side length n, and we'll call this side length 1, which means that theta here is arctangent of n, right? So what happens as n goes to infinity? Now 1 stays a fixed length, but as n goes to infinity, what happens to that angle? The angle gets bigger and bigger and bigger and bigger and bigger and bigger. As n goes to infinity, that theta, the angle, approaches 90 degrees, or in radians, of course, pi over 2. All right, Back to the problem at hand, though. What is it about pi over 2 from which we can draw a conclusion? Pi over 2 is not equal to 0, and therefore the series under consideration is divergent. Okay, for our last example, let's investigate the behavior of this series here. We're not given it in sigma notation. That's okay, we could easily write it in sigma notation if we wanted. Probably not necessary though, because there's enough regularity here where we can just sort of see that we can factor 1/4 out of this and get 1 plus 1/2 plus 1/3 plus 1/4 plus doot. And that's equal to 1/4 times the harmonic series. Well, the harmonic series is divergent. Why? It's the harmonic series. The harmonic series is divergent, right? That's just a beautiful fact. So therefore, if we multiply by 4 or 1/4 or whatever, you're still going to get a divergent series. So that series is divergent.